This is going to go over an introduction to metabolism and enzymes. Metabolism is what keeps cells running. This is the topic for this section of the course. Metabolism involves both building and breakdown reactions. All of this is fundamentally linked to the cell's energy supply, mainly in the form of the ATP molecule. When energy is supplied, ATP is utilized, and a phosphate is released, forming ADP and a P. The energy-producing reactions recouple ADP to P to form ATP. This cycling continues as long as metabolic processes occur. The definition of metabolism is the sum of all the chemical reactions in a cell. The ultimate goal, of course, is for reproduction of the cell and/or organism. Catabolic pathways are the ones that break up larger molecules into smaller products. They release energy. The chemical term is exergonic. These reactions release energy. This is referred to as spontaneous, but it does not equate to fast. Think of how long it might take for a car to rust in your driveway. That's spontaneous, but not quick. Anabolic pathways synthesize or make things. They also require an input of energy. The term is endergonic. They are also not spontaneous. Oxidation-reduction reactions are essential to this system. The chemical slang, or the shortened version, is redox. In a redox reaction, there are partner molecules. One gives, one takes. The donating molecule gives up an electron and sometimes a hydrogen. The receiving molecule picks these up. Cells have specific molecules designated to carry the electrons and hydrogens. The three most important electron carriers in the cell to be discussed in this chapter are NAD+, NADP+, and FAD. You may wonder what exactly these are. They're just molecules, modifications of nucleotides. You don't need to remember the chemical name, just the abbreviation. This image is illustration of a redox reaction. The electron donor molecule passes the electron to an acceptor molecule. The donor is said to be oxidized in the process. The receiver is reduced. If you remember the mnemonic oil rig, for oxidation is loss, reduction is gain, it helps clarify the terms. The loss is of electrons and usually hydrogens, and same for the gain. As mentioned earlier, the purpose of many of the catabolic reactions is to produce ATP for use to power the anabolic reactions. All this attention on ATP, we need some terms. Phosphorylation is the chemical term for adding a phosphate group to a molecule. Remember a phosphate group from the functional group section? Phosphorylating ADP is what the cell does to produce the necessary stores of ATP. Cells phosphorylate ADP to ATP in three ways. One is substrate level phosphorylation. Two is oxidative phosphorylation. And three is photophosphorylation. We'll discuss each of these at various points in this chapter. The whole purpose of producing ATP is power the anabolic reactions that use the stored energy by removing a phosphate from ATP to produce ATP. This image is illustrating the key players in metabolism, the enzymes. An enzyme will bind a specific molecule termed a substrate in the active site. When it does bind, the enzyme shifts shape to clamp down on the substrate to enable a reaction to occur. See this yellow substrate? It fits in the blue enzyme depicted on this right. And notice how the enzyme shifts its shape to better enclose that substrate. This is going to promote the chemical reaction in the substrate, be that a splitting or a joining type of activity. That depends on the substrate or substrates and a given enzyme. Enzymes are catalysts of chemical reactions in the cell. Catalysts are unchanged themselves, but they promote a chemical reaction. Thus, one enzyme can perform many chemical reactions with the substrate. Enzymes are largely composed of protein. The protein component is an apoenzyme. Cofactors, such as ions or coenzymes, like vitamins, are often needed for an enzyme to function. When all of the necessary components are present, this is termed a holoenzyme. Consider your bottle of supplements in your home, something like Flintstones, or in my case, Centrum Silver. The side of the bottle will list the nutrients like calcium, magnesium, zinc, in addition to vitamin D, C, E, etc. What are these? Simply put, they are the cofactors and the coenzymes needed to keep your enzymes functional. Of note, RNA can have a catalytic activity as well. These special RNA molecules are termed ribozymes. As mentioned, catalysts are responsible for driving the chemical reactions in a cell. This graphic is depicting a set of reactants that inherently possess a certain level of energy within it. After the reaction, depicted here, the products contain less energy. The line forming the upper dome represents the amount of activation energy needed to get the reaction going, if no enzyme is present. Activation energy is the energy needed to get a reaction going. Imagine a rock sitting on the end of a cliff. If you kick it, that's the activation energy. It will fall off the cliff and dive toward the earth below. You notice a dotted red line under that larger dome? This represents the amount of activation energy if there is an enzyme present. It's less. And this is why enzymes speed up a chemical reaction. By the way, this is a spontaneous reaction that is depicted because the products have less energy than the reactants, so energy came out. Enzymes are proteins, and proteins rely on their shape to perform their function. You can alter the environment only so much before you affect the folding of the protein and thus its function. The first graphic depicts a rising temperature on the x-axis and the activity of the enzyme on the y-axis. As you can see, there is a point of optimal activity. As you cool or you heat up the environment, you reduce the enzyme function. pH demonstrates a similar effect. Too acid or too basic, you reduce the enzyme functioning. This last graphic has a different shape. It's demonstrating the effect of substrate concentration on activity. You can increase the substrate concentration only so much. At some point, you have maxed out the system and the enzyme cannot produce more products any faster despite an increase in substrate. The activity hits a plateau. This image is demonstrating a particular protein in a normal conformation, and on the right, the same protein has loosened up and unfolded. This state is termed denatured. Denatured proteins aren't functional, and often they can't refold properly once they are denatured, even if returned to an optimal condition. Chemicals other than the substrate can bind an enzyme and interfere with enzyme function. In this image, the pink square molecule represents a competitive inhibitor. Such an inhibitor can bind the active site of an enzyme and block the substrate. The substrate is represented by the clover-like molecule in this image. Competitive inhibitors can be overcome by flooding the system with extra substrate. In this way, you minimize the chance that an inhibitor molecule has the ability to bind the active site of the enzyme. This image depicts a non-competitive inhibition. A non-competitive inhibitor binds the enzyme in a spot other than the active site. This other site is designated an allosteric site. An allosteric inhibitor is another way to describe a non-competitive inhibitor. As you can see in the image, the allosteric inhibitor binds and causes a conformational change in the enzyme such that the substrate can no longer bind to the active site. Non-competitive inhibitors cannot be overcome by flooding the system with substrate. Only when the inhibitor is removed will the enzyme function again. The last concept of this section is feedback inhibition. This is the name for a very common phenomena in cells. In this process, the final product of an enzymatic set of reactions acts as an allosteric inhibitor to the first enzyme in a process. Note that on this image to the left, there's a series of enzymatic steps that work on the product of a previous reaction, using the product to be the substrate that produces another product. The last product in such a pathway is termed the end product. The end product is an allosteric inhibitor of the first enzyme, then shutting down its own system. This is key to regulating substances in the cell. If a cell has plenty of an end product, it will halt the synthesis pathway until it's needed again. That's pretty nifty, don't you think? This particular image from your book is just showing some of the different feedback inhibition systems that are known in metabolism. These are systems that produce amino acids such as tyrosine, phenylalanine, and tryptophan. Well, this includes the introductory section of the metabolism module.